In this video we're going to look at the energy released in a nuclear reaction and the binding energy per nucleon. Pause the video now and try these questions. So if you've read the information at the top, you know that the binding energy per nucleon is greater on the right hand side than the left hand side, because some of the mass of the left hand side has turned into energy, and we've got more stable particles or atoms or nuclei or whatever on the right hand side. So let's work this out. So find the energy released in MeV in this decay, this alpha decay. So step one, we need to find the mass difference between the left hand side and the right hand side. So the mass of the thorium nucleus is 227.97929 U, and then we're going to take away the mass of the right hand side, so that's the mass of the radium nucleus, 223.97189 U, plus the mass of the alpha particle, and we know that U is the atomic mass unit, 1.661 times 10 to the minus 27 kilograms. So if I type that in my calculator, I can find that the change in mass is equal to 9.783 times 10 to the minus 30 kilograms. So this is 4 sig fig, because this is 4 sig fig, my lowest number of sig fig. Now if you get a minus answer here, it's because you've taken the wrong one away from the wrong one. So it should be the right hand side taking away from the left hand side. So if you get a minus sign, make sure you neglect that. So how can we now work out the binding, so the energy released? Well, we know that E equals the change in mass times c squared. So it's 9.783 times 10 to the minus 30 times by the speed of light squared, so 3 times 10 to the 8, which gives us 8.8049 times 10 to the minus 13 joules. If we want to go joules to EV, we divide by 1.6 times 10 to the minus 19 joules per electron volt, which gives us 5.5 times 10 to the 6 EV, which is 5.5 MeV, because one MeV is a million EV. So that gives us our energy released in MeV. That is our answer. Although really, what is my error here? I should have written it to 4 sig fig, so I should really write 5.503 MeV. If we compare the binding energy per nucleon of the thorium and the radium nuclei, what will we get? Well, remember this graph. So if we look at the atomic number, and we look at the so that should be atomic number, and if we look at the binding energy per nucleon, then we get this shape graph here. So thorium is down here, radium is further up, so we can say there is a greater binding energy per nucleon in the radium than the thorium. Radium is a more stable nuclei, which is why this decays in the first place. It's giving out some energy in the form of an alpha particle to become more stable as radium. So this has a greater binding energy per nucleon. Now if you want to work that out as a number, you can check out my other video where I go through exactly that, how to work exactly this out, the binding energy per nucleon of an individual nuclei.